All right. Creepy screen is back up. That means it's time to begin. Hi, everybody. Hi. Thank you for saying hi back. It's actually not a rhetorical comment. Hi, everybody. Hi. Yes. So I finally finished grading all of your SAS homeworks. A few of you, I asked you to fix a few small things. It should take you all of 5 minutes. So please resubmit on the Homework 1 revisions, which is box on Blackboard. Homework 2 and everything else that you've submitted is now updated your points in the online homework system. So you have your current standings for the class available. Nothing to worry about just yet, but I'd like to try and keep that constant for you. Homework 3 is up, although you can't do it yet. So you're going to have to find something else to procrastinate on. You can't use my class. I might suggest cleaning, baking, or Netflix. So it will be up. I had to move the due date because we're about a day behind, so it's going to be due Monday, October 2nd. So 2 weeks from now will be the next one. It doesn't require SAS. It actually just requires a calculator and your brains. So we will see that here in a little bit. If you have any questions about what to fix for Homework 1, please let me know. Most of you made similar mistakes that we've since talked about in class, and so they should be fairly self-explanatory. Any questions on anything before we dive back in? No? Okie doke. Well, we were looking at an example last time. It was these pretend data. 2 groups, treatment and control, 50 kids, sampled pre-test and post-test, the bare minimum of a longitudinal design. So these are the cell means and the marginal means, and the question of interest is to what extent do the kids in the treatment group change more between pre-test and post-test? That's the basic research question. We had looked at 2 models, we had gotten through 3 models actually, starting with an empty model, empty meaning no predictors. How much variance is there to begin with? And we have contrasted a single level model where all of the error variability is captured in one pile, what I call an E only or a between person model. So that total variability in this outcome across all the people, across all the times is about 40. The mean is 53. We then contrasted an alternative model that is different in its model for the variance. So a new letter. What's this thing? What's this U0 thing? It's a vowel. It's a variable. Here's a hint. There's a little I on it. What's the little I doing there? What is that? For every individual. So each person gets their own what? Mean, yes. More technically, what is U0 called? 2-word phrase, first letter of the first word, R. There it is, random intercept. Yes, U0 is the deviation that gets you to your own mean, how far off you are from the sample mean. So by combining the fixed intercept beta 0 that everybody gets with how far off your intercept is, you get your very own intercept as the combination of these things. E then is the difference between that person mean and where you are at any given occasion. So in these 2 occasion data, each person has 2 Y's and therefore 2 E's. How many U0s does each person have? And don't say 2. Yeah, good, say 1. Each person gets 1 mean difference deviation that captures their whole trajectory. Now I have 50 people in this sample. If each person gets 1 U0, does that mean that I've added 50 terms to my model? Lindsay is shaking her head just ever so slightly. She's like, I don't think so, but I don't want to say. Yes, keep shaking your head. No, what have I added instead of 50 terms? because you're right. She's like, I don't know why I'm right. I know that I am. Anyone want to help her? No. This is in the model for the variance, meaning error. What have I added? Instead of 50 things, how many things have I added by allowing that U0 to be part of my model? Nobody wants to talk. See, this is why I'm learning your names, so I can start calling on people. I'm going to call on Charlie in the back. If I add my random intercept, how many terms have I added to my model? How many parameters? 1. See, why didn't you say that before, man? He's like, I didn't want to talk. Yes, 1. Because it's not U0 that we care about. U0 is an idea. It's an idea that represents the idea that we have random intercept variance across people. 1 term. Just like in regression, we don't really care what the E residual is for each person. We care what its variance across people is as 1 term, and we care how much its variance has been reduced by adding predictors. So E is 1 idea, residual variance. U0 is a separate idea, random intercept variance, 2 terms. So we took what used to be 1 big pile of error and we split it. And the model told us that of the total, which is about 40, 12 of that is random intercept variance. 28, the rest of it, is E variance. Let me get my stick. Dun, dun, dun. So here's my R matrix. These are 2 occasion data. That's why I have a 2 by 2 R matrix here. 40 is the variance at pretest. 40 is also the variance at post-test, equal variance. The covariance between pretest and post-test is 12. If I convert that covariance into a correlation, that's the number that shows up in our core down here. That's my 0.3. So that is a very special type of correlation. Exactly. Ding, ding. What's it called? Intraclass. Yes, indeed. So you can think about this number a couple different ways. It's a percentage. It's a percentage of variance that is either between or within. Which is it? It's between. It's a percentage that is between persons, which is level 1 or 2? 2. It's the percentage that is between persons at level 2 due to the random intercept or the residual. Random intercept, yes. It's the random intercept that shows off on the off diagonal that generates the covariance. So 30% of my outcome variance is because of person mean differences, between person mean differences at level 2 that are captured by the random intercept. Another way of saying this is that the expected correlation between pretest and post-test is 0.3. SAS gives us a significance test, a difference in -2 log likelihood that we'll talk about in greater detail today, that contrasts how well the previous model that has only 1 pile fits versus this 2-pile model. That test tells us that that correlation right here, the intraclass correlation, is significantly greater than 0. So yes, 30% is something we need to keep track of. So 30%, one more term, is longitudinal or cross-sectional? Cross-sectional, yes. This data set represents right now a 30% waste of time, I would call. In the sense that The higher the ICC, the more variances between persons, the more variance you would have captured just by measuring them once. So then we looked at predictors. We added a main effect of time, pretest versus post-test, where pretest is the reference. We added a main effect of group, where control is the reference and treatment is the alternative. And we added their interaction term. Do you want to go back over the fixed effects in red there, what they mean? Yeah, why not? Okay, so intercept, always expected outcome when the x's are 0. In this context, because of the way I have set up the model, it is pretest control group. They get 49. Can I talk about the main effect of time? Can I say the main effect of time is 5 and it's significant? No, I cannot. Why not, Aaron? Yes, so if I were to talk about this main effect correctly, what else belongs in my sentence? Something about group. Yes, indeed. So have any of you been taught that you shouldn't interpret main effects if you have a significant interaction? Is that still going around? It is? Seriously? Oh, Claire, you're killing me. Well, okay, thank you for being brave. The first step in overcoming it is to acknowledge the problem. No, damn it, no. You have to interpret the main effects because that's the only way you know what your interaction is doing. There's 4 kinds of interactions, right, folks? More positive, more negative, less negative, and that's it. So yes, Aaron, you have to put in group in the sentence. So I would say the simple main effect of time for the control group, or I could say the conditional effect of time for the control group, but the idea of for a certain group, that conveys the difference. That's the important part. So yes, the control group grew on average 5 points between pre-test and post-test, and that is significant. If I then pair the interaction term with it, that wasn't here, was it, Claire? That was somewhere else in the bowels of your previous training. You can't remember? Okay, just lie to me. No one's trying to pull that here. All right, so yes, the control group grows by 5 between pre-test and post-test. What does the treatment group do according to my interaction term? Does the treatment group grow by 2? What, Amy? It grows by 2 more. Yes, exactly. That interaction term is an increment. It makes that main effect of time that holds for the control group more positive for the treatment group by 2. Charlie? Marginals?
Yeah, but overall, like if you have an interaction, then now you have an overall effect because it's significantly populated by some other term. It's, I don't know, it's meaningless to interpret, but it's dangerous, I guess.
Yeah, so I agree with that. The marginals out here is what they're talking about. You should not interpret these, but I would argue you don't want to interpret these ever anyway. Because if you have an interaction in the model, then these things are meaningless. So yeah, this marginal effect says on average, there is, actually we're on this one, the pre-test, post-test difference is 6.8, but that doesn't apply to the control group or the treatment group, but the average of the 2. But there's no one in the study who got like half treated. So to me that doesn't mean anything anyway, but this is the marginal, that's where that advice comes from. The difference is that when you phrase your linear model this way, some people take that advice and they try to apply it to the situation, even though these are not marginals, these are simples. So we have to interpret these to know what the interaction term is doing. So yes, a caveat perhaps. So yeah, we can go one way with time as the predictor and group as the moderator. Control group improves by 5. Treatment group improves by 5 plus 2. Do we know if the treatment group improves significantly per se? Is there anything on this page right now that tells us this? We can guess because 7 is greater than 5, so if 5 was significant, 7 should be. But in reality, those coefficients are going to have different standard errors if the sample sizes are different between groups. So that's where our friend estimate statements comes in. Let me go back up here. So to get to what the time effect is for the treatment group, come back. That's the second line here. We start with the coefficient for the main effective time. We know that from the interpretation, this is for control. The interaction term tells us how that differs for treatment. So if we start with what it was for control plus how it differs for treatment, we get to what it is for treatment. So it's beta 1 plus beta 3 is what this second line is giving us. And that gets us the 7 that we know the treatment group's time effect should be. And we get our standard error for it and our p-value. There it is. Likewise, my main effective group, can I say that? Can I talk about main effective group without any other words in the sentence? No. When is that main effect valid? The main effective group is 1.6 at pretest, yes, at the reference for time. And we said last time that this being non-significant is actually good news. That means random assignment worked. Hooray, your group should not be different to begin with, otherwise that is a serious problem in interpretation. So there is a group difference that is non-significant favoring the treatment group. That group difference becomes bigger, more positive, by 2 at post-test. So the group difference at post-test should be 3.68 by adding those two coefficients together, plus some change, 3.7, close enough. And that actually is significant as I recall. Yeah. Okay. However, wah-wah, interaction term is not significant, so we shouldn't be talking about it, right? However, this is the interaction term from the wrong model. This is from a model that says that we have one pile of variance instead of 2. This is from a single level model treated for multi-level data. In other words, another way of saying the same thing is that this model says that the occasions from the same person have nothing to do with each other. Unlikely. So we'll see what happens when we fix it. All of the code is exactly the same with one small exception. Let's play Where's Waldo. I have added my random intercept back into my model. Where in the code does that idea show up? Yeah, CS, compound symmetry, is the name for that pattern that says the variance is part U and part E. So now we have what I would call a conditional intraclass correlation, meaning after accounting for predictors. the residuals that are left after controlling for time, group, and their interaction, the residuals within persons are correlated 0.8. Ruh-roh. That means we definitely need this model instead of the other one. We could do a model comparison to find that out. Here is the test for that. Yes, indeed. And lo and behold, the interaction term is now significant. Okay, so let me put the two side by side. I can do it in this. I need a new window. There. The top screen has the model from before, the between-person model, meaning only one pile of variance. The bottom screen has the new model, 2 piles, that differentiates between versus within. So let's take a look and see why the p-value is different. First column, estimate. Conditional mean for the reference group and mean differences. Same or different? Same. Does that surprise you? It's the same model for the means. It's the same predictors and it's the same group means. Degrees of freedom. Now note this is denominator degrees of freedom. Same or different? Same. We still have 50 people. Standard errors. Some are the same and some are not. Errors that refer to person effects, of which we have one, the intercept, because each person has a random intercept, and treatment, those are the same. There's a discussion of this in Chapter 3. The error terms that go along with those between person effects, the numerator has both the random intercept variance in it and the residual variance in it to form your standard error. Whereas the standard errors for time and time by treatment, which are now within effects, only the residual variance, only the E variance shows up in that numerator. So consequently, the standard errors are smaller when you have a 2-pile model for the within person effects. And if you think about it conceptually, it makes sense that it should be this way. The only way to explain how people differ from each other is with people things. People things can't explain why you change over time. In this case, time is a level 1 variable. So we're cutting out people variance in the mean because it's not relevant for testing change over time. It's also not relevant for testing whether groups change differently over time, because it's not about group means, it's about group means over time changing. The time component is the key. So the standard errors are different for the terms that only get tested against residual variance than for the terms that get tested against both random intercept and residual. And that's where we end up with the difference patterns here. How are we doing? Any of that you want to hear again or ask about? Okay. Let me go back up to this model here. Think about what each of the terms mean. So what if instead of thinking of this as a 2 by 2, we incorporate the idea of person as a design element? Anytime you do a repeated measures or longitudinal study, you are in fact doing that. We could have sampled them cross-sectionally over time, but it's a stronger test whenever you can make use of within person information. So if we think about it from that perspective, we have a 3-dimension design, person by time by group. In a 3-way design, we've got 3 main effects, 3 two-way interactions, and 1 3-way interaction possible. So which of these terms have been included and which haven't? Do we have a main effect of time? Not a trick. Do you see one? Do we have a main effect of time? Like that thing, perhaps? Can I get some nods or something? Come on, folks. I know you don't want to talk, but no one's going to see you nod, I promise. Yeah, okay, thank you. Do we have a main effective group? Do we have a main effective person? Not in red. That's this thing. That is a main effective person, folks. It's allowing each person their own mean difference, right? It's a random main effective person rather than a fixed main effect. It's carving out a pile of variance that is attributable to person mean differences rather than talking about person 1 versus person 2 versus person 3 as fixed effects. Now let's look at the 2-way and 3-way interactions. Do we have a 2-way interaction of time and group? Yes, we got one of those. Now given this design in which each person is in only one group or the other, can we do person by group? Is that possible to test? In this design, you're in either one group or the other. Can we do person by group? No, we cannot. Person by group would imply how the same person does differently when in the control group versus the treatment group. We can't see that. The design doesn't afford us that. So if we can't have person by group, we can't have the 3-way of person by time by group. That leaves one more term. The other 2-way interaction we haven't talked about yet is person by time. Do we have that or not? This is a tricky one. Erin's nodding. She looks confident. What is it, Erin?
Well, since they can only be in one group, if we did it by treatment, time by treatment, that's...
Nope. Person by time. Right, but each person gets to change over time in their group. Person by time would say that some people improve more than others. On average, the groups change by this much or that much, but some people in the control group might change more than other people in the control group, for instance. That thing? The interaction group? The interaction term and the time term would have reduced this variance. It came out of there. Yeah, so, but you're on the right track. What's this thing mean? You're used to thinking about E just as this thing that's at the end, right? It's person by time, folks. That's what's left. That's the only thing that it can be, is the idea that each person might need a different rate of change. The model up to this point went from no change at all to at least some kind of change on average. That's the main effect of time. And then differential change on average as a function of which group you're in. On average, the control group changed by 5 and the treatment group changed by 7, but not everybody followed that pattern. So if you changed more or less than the rest of the people in your group, that's unexplained variability, and that's E. That's what's left. This is meant to illustrate why ANOVA is just fine for 2 occasion data. There is no way to differentiate individual differences in change, the idea of that person by time interaction, from residual. We don't have enough information. Let me show you a picture here. No, I don't like that. That. So you've got 2 choices. The way the model is set up right now is on the left. Let's say that these are 2 people from the same group, so they both have the same predicted rate of change. Each person has their own random intercept, the U0I, for how far off their mean is from the grand mean. They each get the same slope because they're in the same group. That slope doesn't perfectly account for all of the variation for each person. So we still have these E's as how far off each occasion is from the predicted line. So we can either say that we have residual variation over time and each person gets their own intercept, or we can say, yeah, each person gets their own intercept and they get their own slope. That's what the picture on the right is. But how well does a line fit 2 points? Do you remember this from geometry in like 9th grade? How well does a line fit 2 points, people? Lucas, you're smiling at me. How well? Perfectly, right? So from a mathematical perspective, this is 6 of one, half dozen of the other. You either have perfectly identified individual differences in change, or you have residual, but not both.
We'll say that again.
Yep. If you have 2 occasion data, you can either call the variation that's left over around the lines E residual variation over time, or individual differences in change. You can't actually test whether you have individual differences in change. If I had 3 points, then I'd be in business. If I had 3 points per person, then each person could have a different slope than the rest of their group, and we would have enough variation left over to judge that against E variation. As an aside, there's a particular flavor of bullshittery going around called latent difference score models. When estimated with 2 occasions, this is what they do on the right. They shut off the residual variance and they put all of the variance up into some triangle or some shit like that. And they say that people change differently and it's a latent difference. No, there's nothing latent about it. It's just a difference score. That's fine. If you have 2 occasion data, rather than having pre-test and post-test as 2 separate outcomes, it may be more convenient for you to have, say, a pre-test variable and a change score variable. There's nothing wrong with that. With 2 occasion data, that's all you can do. The problem is that that change score is not measured very well. You don't have a lot of information about change if you only measured 2 occasions. It's way, 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 way better to have 3, 4, or 5. But if you've only got 2 occasions, this is all you can do. ANOVA is fine. The rest of this just shows you what the output would look like if I used the class statement instead, where I could ask for the group means and group mean differences via LS means. So it's just less typing to get a lot of the same information just for pedagogical purposes. Okay. How are we doing? Yes, ma'am.
So where did she see that the air went down? Like, so it's because you did the condition, the compound symmetry thing, right?
So 2 different things here. error went down, meaning variance is explained. Is that what, Amy, is that what you were talking about before? Okay. So we can think of it a couple different ways. If you look at the single level model, it went from 40 to 27. So we could compute an R-square for that. The problem with the single level model is that all of the terms related to time are not being tested with the right standard error, and so they're suspect. Now the same is still true if we look at the two-level model. The total variance left over is still 27. The difference is how much of that 27 is attributable to level 2 versus level 1, is attributable to between versus within. And what this is saying is that of the variance that remains in this outcome after controlling for time and group and their interaction, most of it is between. So the model did a much better job explaining time level variation than it did explaining person level variation. Now, a crazy thing that you may not have noticed, but I'll point out to you, in the empty model, the partitions were 12 and 28. That was our original intraclass correlation of 0.3. In the conditional model with my predictors, the residual went from 28 down to 4. Because the residual went down so much, my random intercept actually went up from 12 to 22. And yes, that sounds screwy, but it can totally happen because of the way these things are being estimated. We'll talk about that in a couple weeks. That's part of the reason why R-square is such a difficult thing, because this type of variance increase, when you explain variance at a lower level, happens very commonly. So most of the variance that was explained by the predictors was at the time level. Of the variance that's left, most of it then is at the between level. Now, does that help? Okay. All right. Other questions? So these two models that I've shown you right here are two different kinds of analysis of variance. The one-pile model, E only, is what you would call a between groups ANOVA, or independent ANOVA, between subjects. Can you think of any other terms? I don't know. One pile is what I'm going to call it, E only. When we add a random intercept, where we ended up here, when we fit this compound symmetry R matrix, where we're saying that part of the variation at each occasion is due to random intercept at level 2, part is due to residual at level 1, that is what's called repeated measures, the univariate version. There is a third out there, which is a multivariate version. So I want to segue into presenting these explicitly, how they differ and how they are the same. That way, when some well-meaning advisor or collaborator or reviewer says, why do you need all these fancy models? Why don't you just do an ANOVA? You can give them a thoughtful response. You can explain why you need it, or you can say, well, actually, this is the same thing as an ANOVA, just using maximum likelihood, for instance. That might be one of the things that happens. So I'm headed back in lecture 3 on slide 17. So there's 3 kinds of ANOVAs: between groups, E only, repeated measures, univariate, which is the E plus U, and a multivariate version, which we'll see in just a second. They all suffer from the same limitations. Because they are estimated in least squares, they do listwise deletion. So when people talk about ANOVA being bad per se or inappropriate, what they really are talking about is a combination of 2 things. The worst thing is the least squares problem. Having to throw away any partial data is a bad idea. So it's not ANOVA the model per se, it's the estimation that requires listwise deletion. None of them allow time-varying predictors that are continuous predictors, and all of them have the same type of means model with respect to time, which is called a saturated model. It's the idea that you spend as many degrees of freedom as you have occasions. You allow each time point to have its own mean. So what happens if your people don't cooperate? What if instead of coming back at time 2, they came back at time 2.5? This saturated means model that is inherent in all of the ANOVAs cannot handle that, because time is being treated as a categorical predictor, not continuous. It has to be rounded into convenient intervals. So least squares is bad news. This requirement that time has to be categorical and balanced is bad news. The way that ANOVAs differ from each other is in their model for the variance. How they handle dependency, how they build in a pattern of correlation for the occasions that come from the same person. There are 3 different options for what that correlation should look like. Here's the first one that we saw, the single level model, the E-only pile model, single pile model, an R matrix that in SAS you would specify on the repeated line as VC. That means variance components, all the variances are equal across occasions from the same person, and there's no covariance whatsoever. This is an independence model. This is the same as like a linear regression type model. Just if you have categorical predictors, you'd call it ANOVA. This is likely to be very wrong because occasions from the same person usually are correlated. So here's the one that we just looked at as an improvement. The univariate approach to repeated measures, the 2-pile U plus E version of the model. That prediction that those 2 piles create is called compound symmetry. That's the name of this pattern. Compound symmetry says all of the variances are the same across time. So they're part U, they're part E, and it's all the same way across time. And all the covariances are the same across time. So times 1 and 2 are just as related as times 1 and 100. The idea of these random intercept variances being on the off diagonal where the covariances are, what this is saying is that the only reason that occasions from the same person were related is because of these person mean differences. Those person mean differences are captured by random intercept variance. Once you adjust for that, the E's are unrelated. People differ from each other in only one way, and that creates a growth pattern that looks like this picture on the left. Parallel lines. That doesn't happen very often in longitudinal data. So if people grow at different rates, what happens to the variance across time? Same or different? Different. Different somehow. Different how depends on the pattern in your data, but the point is the only way that compound symmetry can hold, that can be appropriate, is if people all change the same. So if you have 2 occasion data, you have to believe that they all change the same because you can't separately identify individual differences and change from residual. That's why ANOVA is fine for 2 occasion data. Now, to the extent that you have some people who didn't come back on post-test, you'd still want to estimate your ANOVA using proc mix with restricted maximum likelihood. That way you could keep everybody in the sample that has as much data as possible. You would keep all the pre-test scores even if they don't have a post-test score. Those people who have incomplete data, their data would help estimate whatever parameters they could contribute to, just not the ones they don't have data for. So this is why ANOVA is potentially problematic for longitudinal data. It does not allow individual differences in change as another reason why there should be covariance across time. or differences in variance across time. Now I have to get into a slight aside. Sphericity, blah, 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 blah. There's my take home. On your ANOVA output, you get tests of sphericity. Mochley, maybe, or Murray, I don't even remember, some other dude's name. They have tests for whether or not sphericity holds, and at least I was taught if those tests are significant, meaning it doesn't hold, you're supposed to go look at the other set of output down below. Well, those tests are based on this idea of whether or not pairwise differences have equal variance and covariance. That's what sphericity is. There are various approaches people have developed to try and correct for violations of sphericity, but that's like putting a Band-Aid on a broken arm. It doesn't really address the problem. It only addresses the problem in the best way that you can with least squares, which is not very good. So when compound symmetry doesn't hold, when you have individual differences in change that cause differences in variance, or when you have differences in covariance over time because your occasions are more related if they're closer together than further apart. So basically, anytime you have longitudinal data, this is not going to be enough. The only other option that you can have in the world of ANOVA is the other kind of repeated measures ANOVA, which is the multivariate approach. This is also known as Manova. When people use those words, odds are good they're still talking about least squares. The Manova model itself, though, is not actually a model. It is the answer key. It is always right. It cannot be wrong, by definition. What this model says is, I don't know what this pattern should look like. Let's just let everything be what it wants. Let's just estimate every single variance at every single occasion separately. Let's estimate all of the covariances separately, and let's let this just be what it wants. Now, those of you who've been through SEM have heard these words from me before, or other people before. What's the analog in that world to this model? Anyone? It's not the HO, but the other one. Anyone? Bueller? Anyone? It's the H1 model in SEM. It's the everything gets to be what it wants. This is the answer key. This is as good as it gets. So rather than trying to approximate the pattern of variance and covariance over time with some simpler version of the model like U plus E, it's like, no, we'll just let it be what it wants. So the good news, this can never be wrong. The bad news, you can probably never get to use it. Here's the problem. The number of parameters that it takes to estimate this thing is, you may recognize this as the formula for degrees of freedom in the world of SEM. Number of occasions times number of occasions plus 1 divided by 2. So if I have 10 occasions of data, for instance, that's 55 parameters before I put anything in the model that I care about. That means at a minimum, I need to have at least 55 people to estimate that thing. Ew. No. If you only have 2 or 3 occasions, this is probably fine. Go with this. You have my blessing. Do it in REML so that you don't have problems with incomplete data and so that you can do time varying predictors, but do this, that's fine. Charlie.
What about overfitting?
Yes. So statisticians would yell at me for saying you have my blessing, because the more parameters that you estimate, the larger the standard errors are going to be for each of them. That's why even if I can do this model, I typically look for something simpler that fits not significantly worse. But there aren't a whole lot of choices that would be viable if you only have a couple occasions, and there's not that many parameters either. If you have 10 occasions, I would not stick with this unless I had like thousands of people and absolutely no other alternative I could come up with fit. Now the other reason you can't use this, what if you only have a couple of occasions but people didn't cooperate? So I'm talking about these matrices as if time is a rounded interval, right? Time 1, time 2, time 3. Where does time 2.5 go in my matrix? How about time 3.75 or 4.9? This model only holds when you have balanced data. Everybody shares the same time structure. So when this is possible to estimate, we will use this as the answer key with which to compare other simpler models, hoping to find something that is not worse than this, something simpler that can approximate this structure, because this is as good as it gets. But this is only possible when you have balanced data and you don't have too many occasions relative to your number of persons. So can I tell you a story? I think our energy is flagging. I'm very sympathetic to those of you who may have to deal with people in your future who haven't had the opportunity to take these courses and may argue with you about the necessity of certain things, such as well-meaning reviewers. I once had a student who was a frequent flyer in my office hours working on her dissertation, and she had 3 occasion data. It was pre-test, post-test, and like a follow-up. So she had a trajectory that she hoped would look like this. Only problem, half her people did not come back for follow-up. Happens, right? Lindsay's like, oh, I know, right? This happens. Yeah, these were real people. She was actually in a clinical setting working with people with severe mental illness, and like, you know, stuff happens, right? It wasn't an experiment in the sense that anything she could control. So because she was expecting a trajectory that looked like this, and she had 3 occasions, and they were balanced enough in the sense that this was before, this was after, and this was like more after. She measured them pretty much at the same time. I told her she should just fit a saturated means model, meaning put these 3 occasions in, and we phrased the difference here as one slope and the difference here as another, and so she could predict who changed more initially and who was able to maintain with whatever predictors. She also had some time varying predictors, fidelity process kinds of like how many times did you actually go to your group that you were supposed to go to kinds of variables that were time varying. So for those reasons, I set her up with proc mixed, and she went and ran stuff, and she did not have very many people and nothing was turning out significant. And her advisor was like, you know, I know Lisa's been helping you, but I don't think you have enough data for these fancy models. I think you should just see what happens if you do an ANOVA. And she came and relayed this advice to me, and do you know what I said? Anyone? Nah, that's a good one. No, I would have said that, except first I had to lose my mind and be like, this is an ANOVA! What she had done in proc mixed was a saturated means model. 1 intercept and 2 slopes gives me 3 means. She ended up having just a random intercept because it did not fit worse than the everything gets to be what it wants model. That one. And so functionally speaking, from a modeling perspective, the ingredients she put in, a random intercept, a residual variance, and saturated means, that is a univariate repeated measures ANOVA. She did an ANOVA. Now, why would I lose my mind? Because the difference is that she ran her ANOVA in proc mixed. Had she run her ANOVA in whatever ANOVA from SPSS or proc ANOVA in SAS or whatever ANOVA is called in Stata, what would have happened? Yeah. Which is terrible, exactly, yes. Complete data would have been required because least squares versions of ANOVA require complete data. Now the other piece, she had time varying predictors. There is no place to shove them into the ANOVA model when it is done via least squares. So she couldn't have answered some of her questions about her predictors. So now you understand, I lost my mind! So the other side of the story then is I've had students who went the opposite way. They got to my class and they were feeling superior and said, hey, I'm going to publish papers using MLM now and I'm going to show the rest of my field how it's done. So I got to read a draft of a paper one time and this person was like, oh, you dumbasses are still using ANOVA and I'm going to use MLM and show you how it's done. And then you get into the modeling section and the person tested for random slopes and none were significant, so they stayed with a random intercept. My response, once again, say it with me. This is an ANOVA! No, you don't get to be superior because you learned how to use proc mixed. No. If all you have is a random intercept, that is still an ANOVA model. The nice part about it, though, is that at least this person tested to see if he could improve on it and found that it wasn't going to be improved on and that it was sufficient for their data. So the moral of this story is that there's nothing wrong with ANOVA per se. The problem with ANOVA is least squares most of the time. Where ANOVA goes astray is when you try to fit data into it that don't belong. When people don't cooperate, and you have things like time 2.5 and 3.5. When you do a longitudinal study that has lots of occasions. So a couple of you work with Chris Cushing. Anybody in here? Yeah, a couple of you do. He has like 80 occasions per person, right? You think that's going to fit in here? No, it's not possible. Does that mean he should give up and go home? No, he needs tenure. So we got to keep moving on. Yes. If you do the appropriate tests that I'm going to show you and you find out that this is sufficient, for instance, the compound symmetry model is sufficient, you have my blessing to use it. The question is whether or not this is good enough. And if you have individual differences in change, this is not good enough. If you want to go with the other ANOVA model that you got taught, or maybe didn't get taught, the repeated measures, this one, this is only possible to do sometimes, and it still requires complete data. So what I want to give you are more choices. There's no reason why you should be stuck with only these two options for all of the world of longitudinal in your arsenal. There's way, 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 way more choices. So the rest of the course is focused on adding to these two, not taking away from them, because we'll see that these are important baselines. But we're just going to fill in more options relative to everything has to be the same, which is what the random intercept model says, versus everything needs to be completely different, which is what unstructured says. All right, I got to calm down. Questions? Sir? Yes.
What do you do when your data does have that 50 by 50 matrix?
Oh, that is the most perfect segue into the next part of the lecture. Thank you. Let me answer that question. Whether or not everything needs to be what it wants is necessary is a testable hypothesis. So it's the idea of model comparison that we get to. How do you answer that? What we're looking for is something that is not more complex than it needs to be, just complex enough. That's always the goal. Yeah?
But you still have to fit that piece to the model.
Well, if you can. SAS just may give up and throw up, in which case that's not an option.
Can you tell a journal that this model couldn't fit, so therefore...
Yes. The unstructured model would not converge. Therefore, we had to go with something else.
It won't say, well, you tweak your software or run it on a cluster with...
It's not a speed of computing issue, it's the amount of information issue. If you don't have a lot of occasions, or excuse me, if you have a lot of occasions but not a lot of data, you may not have enough information to get all of it estimated at once. So the question then is, well, if you can't do that, what are some plausible alternatives that you can get away with? And it turns out there's quite a few if you move into the world of mixed models, random effects, and alternative covariance structures. So then the question is, how do we know which ANOVA is the right one? And then more generally, how do we know when those aren't good enough and we need something else? So whenever we were talking about interpreting fixed effects, right, like in this example, effects of time and group and interactions and stuff, I've just been staring at these p-values. What are these p-values called? Because you can't write in your method section, I stared at a p-value. How did you judge the significance of fixed effects, people? What are these things called? Wald test, yes. Modified Wald test because they're using denominator degrees of freedom, yes. These are all Wald tests. If you have an F instead of a T, that is a multivariate Wald test. The bad news is that we can't use these same p-values that show up for variance terms to judge their significance. That's because variances can't be negative. So if I have 0 over here, and I'm testing the significance of a variance, here's the sampling distribution for it. The estimate would be in the middle. We would look at 2 standard errors on either side, and we could say whether or not this is different than 0. That's fine. However, what if we were testing a variance that was a really small number, and 0 was here? What's the smallest variance you can ever have? 0. So the idea that we could take a Wald test and go plus or minus 2 standard errors around it doesn't work. And the closer you get to 0, the more it doesn't work. It's on the boundary. So these Wald test p-values that show up here under covariance parameter estimates, you are never to look at, ever. Here's what to do instead. And when I say never ever, I mean there's like 20 people in the world who know the difference, and I don't want any of them to yell at you. I'm trying to teach you the right way to do things just in case somebody who knows the difference ever evaluates your work. So what we're going to do instead is look at model fit. It's going to be relative model fit most of the time, meaning that we'll look at one model relative to another. There may or may not be the right answer to compare against. But in these models, relative fit is indexed by the overall model's log likelihood, which you will get into more technical definitions in Chapter 5, but for now we can just say that it is the sum across persons of the log likelihood of their data given the best case model parameters. So the number that shows up on SAS, in SAS output, as well as in SPSS, is minus 2 times that number. So this is where job security kicks in. Log likelihood is an index of height, meaning how probable is it that you'd observe these data if these were your model parameters. You can't say probability because it's a continuous distribution, but that's kind of the idea. Height is taller is better. So if you're looking at output in which you get log likelihood, bigger numbers mean better models. But that's not what we're going to be looking at. We're looking at log likelihood times minus 2, which flips the direction, so smaller is better. It's lack of height in these models. And we have 2 flavors of maximum likelihood, the regular flavor or the restricted version. REML is the same thing as least squares, by the way, if you have complete data. That's the version that we're going to be using most of the time because it's best for small samples. So to compare models that differ in their terms for the variance, such as, do I need a multivariate repeated measures ANOVA, an unstructured, or can I get by with just a random intercept? We're going to do likelihood ratio tests. These show up in a lot of areas of statistics. They show up in the world of CFA and structural models. They show up in IRT. They show up in logistic regression. They show up in a whole lot of areas. And what we're doing is comparing the -2 log likelihood difference across models. So it is always phrased as the -2 log likelihood from the model with fewer parameters, meaning the simpler model, minus the -2 log likelihood from the more complex model. If you are given log likelihood in your output instead, then you have to take the difference in the same order and multiply it by -2. The reason that the -2 shows up in here is because -2 times the difference gives you a distribution that it looks like a chi-square. So the difference in -2 log likelihood, we compare to a chi-square distribution with degrees of freedom equal to the difference in model parameters, and then that gives us a significance test, whether the terms we've added help the model. Stata people, you can get a likelihood ratio test option within your program. I have given you several examples of Excel worksheets that I use chi-dis to get an exact p-value for these things. I'm sure there's other ways to do it as well. So here are your decision rules. If we're talking about adding parameters, for instance, if I go from an E-only ANOVA model to a compound symmetry, meaning adding a random intercept, the model fit can either get better or not better. If it's significant, if the difference in -2 log likelihood is significant, then it got better. If the difference is non-significant, it's not better. If I'm taking parameters away, so if the comparison says unstructured, can I get by with something simpler that fits almost as well, like unstructured versus random intercept, then it's going to be worse or not worse. Worse means significant, not worse means non-significant. We also get these things called AIC and BIC, which are permutations of -2 log likelihood that correct for the number of parameters, as well as the log n here. This is level 2 sample size. I just corrected this on another slide, but you can add that here if you want. So that big N stands for level 2 sample size. And those should be used as converging evidence, but they're not significance tests. Smaller is just better. There's no cutoff, there's no rules, it's just smaller. So we tend not to use those if we don't have to. So that, on the example that we were just looking at, is what SAS does for you in the case where you're comparing an E-only model, one pile of variance, to a model that has 2 piles, adds a random intercept. So if we compare the 1 pile model that has all our predictors in it to the 2 pile model, the -2 log likelihood from the 1 pile model was 602.5. After we added our random intercept, that went down to 544. 602 minus 544 is 57.8. That's a difference of 1 degree of freedom because we added 1 random intercept variance. The critical value for 1 degree of freedom for a chi-square is 3.84, so 57 is, yes, bigger. And this gives us an empirical means by which to pick amongst competing models, or to answer people who say, do you really need something that complicated? You can say, well, it fits better, so I guess I do. Either way, you can do it yourself in Excel, or I wrote you a macro program that does it. The same little deal that you used to calculate total R squared, where you save output and it does the math for you, I wrote another one for that. So yes. Yeah, I got tired of typing in Excel too, so I wrote that a long time ago. So yes, so whenever we are adding or subtracting terms from the model for the variance, this is what we will do, differences in -2 log likelihood. All right, we don't need to talk about that yet. So very briefly, the ANOVA handout, you can look in your book, the end of chapter 3 is talking about this. I just wanted to give you the code that shows what things look like. This is example 3B very briefly here. Session as a categorical predictor, 6 occasions. Type equals VC gives me my between groups ANOVA. That's my E-only variance model. Type equals CS gives me my univariate repeated measures ANOVA. That adds the random intercept to the model. Oh, Amy, this is I'm already using my macro here, by the way. It's right here. ODS output, save the fit statistics to a data set. We'll go back over this next time, but just so you see it. And then last but not least, multivariate version of repeated measures ANOVA. Another 2-letter difference. UN stands for what? Unstructured. Everything gets to be what it wants. Answer key model. I can do it in this case because I have balanced data across 6 sessions and enough people to pull it off. And here are the log likelihood comparisons. Excuse me. Nope, here they are. My macro did for me. -2 log likelihood from the between groups ANOVA was 9155. -2 log likelihood from the compound symmetry, add the random intercept model, is 8353 for a difference of 802. Yes, random intercept helps. Is that good enough, or do I need to have something more complicated? I have 8353 versus the everything gets to be what it wants. Everything gets to be what it wants wins by a difference of 123. So of the 3 possibilities for this little example, multivariate wins, but this is going to be the basis of what we do in chapter 6 to see if we can do something that gets as close to unstructured without being this complicated, because it takes 21 parameters for 6 occasions to fit that thing. So, point being, empirical question, whether or not you need the additional complexity. All right, so we'll look back at the F values and things for that next time. Otherwise, we're done for today. So office hours start now, although I don't know that you need to talk to me. I'll hang out in case you do. I shall see you all next time.